know how I like that camera. I'll leave it on. See. Okay, so I just wanted to show you this. You can read it, I'll explain it. But let's go top to bottom. So this is for linear algebra done right. Chapter 2a, span and linear independence. This is where I kind of hit a roadblock for a bit and had trouble understanding the proofs in the textbook, but I got through it and I'm here to share what I've learned. Okay, so the two proofs that I got stuck on are the linear dependence lemma. There's a difference between independent and dependent, so linear dependence lemma. And then the length of a linear independent list is less than or equal to the length of a spanning list of a list of vectors. So I'll go through that. Those will be the two last things that we talk about. The homework is every multiple of 4, so 1, 4, 8, 12, and 16. And I guess let's get started. So what's span? Because we're doing span and linear independence. So I learned that span is the set of all linear combinations of a list of vectors. So linear combinations, I believe that should be pretty easy to understand. If you don't understand it, it's basically you have a list of vectors, right? Vector 1, 2, 3, 4, 5, 6, 7. Okay, linear combination. You take a scalar and multiply it by you take a set of 7 scalars and multiply it by those 7 vectors, and then add them together. That's a linear combination. It's like the first thing in the chapter. I found that easy to understand. If you don't understand it, go to the Rakugaki in the description and either leave a comment on the video or open a question in the forum on the Rakugaki. And if I see it, I'll try to answer it. Okay, so the span is the set of all linear combinations. So if you have a vector, I'm going to simplify this in F3. So you got your y, your x vector, and your z vector. If you haven't seen it, you can do it with your hand like this, right? So I got 3 vectors. The span of these 3 vectors is the entire space. Let's actually make this over R3. So these are real vectors. The span of this is your entire space, R3, right? Because any multiple of your x vector plus any multiple of your y vector and plus any multiple of your z vector, combine those, you get any point in this 3-dimensional space, right? So the span of those vectors is the span is every vector in this space, which is the vector space. So that's what it means when a vector list spans a vector space. It means that the span of that vector list creates every vector in your vector space, right? The span creates every vector in your vector space, and that is your vector space. Okay, so that's like my simple layman's term explanation, which that's how I figured things out and learn it. I'm hoping it translates over video. Then the next thing was a polynomial as a vector space. How does that work? Well, it's just the set of all polynomials up to an nth degree. So you recorder cut out. so you have a polynomial of nth degree, and so you have your variables. So I learned it polynomials, I usually use x. So you have your constant plus something, constant x plus constant x squared plus constant x cubed, and so on. That's your polynomial, right? So here it's using z or z in Sheldon Axler's textbook, but the basic idea is the same. So your vectors are the z's, right? And then you have a linear combination of those vectors, which is your constants, and your constants are from the field f, so real and complex numbers. And the notation to denote that is polynomial of, and then f, so the what field it's over. And then I found this video. It was incredible because it goes through the entire chapter, and actually it missed the last proof, but I figured that out by myself after watching the video, so it was very helpful. I'll link it in the description, and if you check the Rakugaki, I put the video link for every single chapter if it helps. And here we've got at 29 minutes and 33 seconds, he talks about the intuition of spanning and linearly independent, what they actually mean. So you got the basic idea, but linear, so you got the basic idea spanning. I explained that with the 3 vectors, and it makes every vector in your space. But the intuition between linear independent is you want 3 vectors where you can only make every vector in your space by combining this vector, and this vector uniquely. Okay? So if you had this second example here, if you had 2 vectors going in the same direction, I'm going to delete the z vectors so that we just have x and y. If you have 2 vectors going in the same direction, so you've got x, y, and I'm going to call it z, but your z vector is now going in the same direction as y. If you got 2 vectors, you can make the 0 vector 2 ways by having 0 of x and 0 of everything else, so all zeros, or you could have 0 of x and y and then minus y. So that's not a unique way to create every vector in your space, right? You can create vectors in multiple ways now. Like this vector here, the z, sorry, I said negative y, I meant negative y minus z. This vector here, z, can be created by x and y now, and vice versa, you can create y by z and x. So nothing's unique anymore when you have colliding vectors. So you want a vector that creates every vector in your space, and you can do that by having vectors that point in totally different directions. So that's linearly independent. Okay, now on to the first proof or lemma. That was the big confusion. Okay, it's not scrolling. I'm gonna stop the screen recording and come back. And we're back. So now for part 3 now, because it keeps not working. I'm gonna have to sort this out. 2.21 is the linear dependence lemma. So this is a lemma with 2 parts. So I made some mistakes when I was reading this lemma, and first is not noticing that it said linear dependence. I thought it was independent. So in case you made that mistake, this only holds if your list of vectors is linearly dependent. And go back 10 seconds to see me talk about what linearly dependent means. So, okay, I've written it here. Multiple linear combinations can make the same vector. That's what it means. And this lemma, if you read it closely, it's saying that there exists Vj such that A and B hold. Not that any vector in the list, you can take any vector in the list and A and B will hold if it's linearly dependent. It just means there is one vector, there exists one vector in the list. You have to find it where A and B hold. Okay? So those were my mistakes for the linear dependence lemma. And here's the intuition for A. So this is how I take notes. I read it and then I read the proof maybe, but doesn't really click. So then you talk about the intuition. You try to intuitively think about it. And here's the intuition for A. So A states that if you take a list of vectors and they're linearly dependent, right? Vj, so you take the point Vj in the list, then the span of the previous elements, so there is going to be an element Vj where the span of the previous elements contains Vj. Because think about it, it's linearly dependent, which means multiple linear combinations make the same vector. So at some point you're going to have a vector where the previous vectors are a linear combination that make the same vector at the end. So, okay, maybe that's not a great explanation, but think of the three vectors in the same plane this time. So you got three vectors in the same plane. If you make a list of them, you can always linearly combine two previous vectors to create the last one. So you can always combine these two vectors somehow because they're in the same plane. It's like x and y axes. You can combine the x vector and the y vector to create any other vector in that plane, which means you can use these two vectors to create any other vector in this plane, which includes this vector, right? No matter how you combine this, if they're all in the same plane, you can have two vectors that create the third vector, right? So that's the idea. The intuition for part B now. So if you can create Vj from linearly combining previous vectors in the list, you can remove it from the list and the span will remain the same. Does that click, or is it a bunch of words? Okay, when I read it, it is a bunch of words, but the idea is extremely simple. So if you have your previous, so for part A, you know that Vj can be made of the span of previous vectors in your list, right? If that's possible, if Vj can be made from the span of the previous vectors, then you can take out Vj and the span of the previous vectors will include Vj anyways. So you can remove it and the span will remain the same. That's the idea, okay? That's as simple as I could condense it down to. Hope that helps. And then now for proof 2.23, the length of a linearly independent list is less than or equal to the length of the spanning list. This is a list of vectors, by the way. It doesn't say that. It's a list of vectors. So you have your list of vectors. So 1 through, I don't know, 10, right? List of vectors. So the length of that list of vectors. So first, it's linearly independent, which means you can only make the vectors. There's only a unique. So there's one unique way to combine the three vectors, or the vectors in that list, to make a new vector in the spanning list, right? So that means that there's only one linear combination of the vectors in the list. So there's only one way you can make each vector in the spanning list, which means that so you got 3, and then you've got every vector in your spanning list, and there's a lot more vectors in your spanning list. It's very hand wavy, I know, but that's the intuition behind it. So we've got the less than part, but when does it equal the length of your spanning list? Remember, every linear combination creates a vector in your spanning list. There's only one way to do it. So how would you make it equal? Well, what if you have only one vector going in one direction? Well, the only way that, first of all, there's only one linear combination, right? No, there's not. Okay, let's take the null space. There's only one way, one linear combination of that null space, right? Yes. The null vector, sorry, whatever it is. And then the length of the spanning list is that one linear combination, which means it's equal. That might be slightly scuffed, but I think it's an example of when it equals. Okay, so that would conclude my notes from Chapter 2a, Span and Linear Independence. If you would like, or if anything is wrong, please let me know. And I'm really hoping this helps. You can see more resources and some written notes on this, additional written notes if you still need help. And check out the forum on, that's nice, on Rakugaki, the Genius app, where this will be uploaded. So have a great day, and I will see you